Hi guys, my name is Rohit Singh Chauhan, and today we are going to shoot our first episode in a series of podcasts that we are going to shoot for the Calance Data Team. In this series of podcasts, what we are going to do is we are going to cover different topics related to different branches of the data division that we serve here in Calance. One of the key divisions that we have is the data sciences division. And in this data sciences division, we are very aggressively moving towards hiring talent and giving services in the generative AI field. So today I have two experts with me who are working primarily with the Calance team. One of them is Palash Jain. Now, Palash Jain is a senior manager at the Calance Data Sciences division. He's handling the generative AI and the machine learning team that we have built here. And then we have Rishi Patel, who consults with us and lets us know about different technologies and different spaces whenever we deliver certain very key projects related to our US clients. And Rishi also has a very unique capability in the sense that he has built his own company, which is called MeetMinutes. MeetMinutes is a generative AI chatbot which can summarize different videos from different inputs and then essentially give you a transcript of all the different videos that you have captured. And there are several different capabilities to the MeetMinutes product, which we'll discuss later on. And I definitely want to show you the applications that we have built here as part of the Calance data division, of which Rishi can explain us a little bit more about the projects that he is doing. Palash can also tell us some of the projects that he is doing. And I'll be leading them through different techniques of how you train an LLM, what exactly is an LLM. And yeah, I think we can just jump into it. Right, guys? Yeah. Sure. Okay, so before I go into the podcast, one thing that I would want to give an experience to the user is how exactly a large language model is built. But before going into the building of the large language model, I think it's essential for you to understand that what exactly is a large language model. Now, a large language model, as the way I see it, is a very complex set of a very complex architecture built on neural networks. And that complex architecture is essentially able to understand very beautifully indeed the human language. And we have been doing this as a human species. We have been trying to understand language since the past 80 years, ever since AI came into the picture. But because human language in itself is a very complex field, we only recently have started gaining exposure into how we can model it using artificial intelligence. Now, a large language model right now is the backbone of the understanding that we have built in the AI field for human language. And the way I understand, again, a large language model is it's kind of a specific model which helps you go through the entire language as if you are actually interacting with another human. And that the level of complexity it is handling right now, it's absolutely brilliant. And the complex architecture that we have behind the neural network, I'll move into that with Palash here right now.
So to start with, I think we should think of a language model, a large language model, as a language expert that sits on your computer.
Okay.
Right? It's not only very smart in understanding what you say or what is written in some texts, it's also intelligent enough to talk back to you.
Okay.
And that comprehensive understanding of language allows it to do a variety of things, like summarizing texts for you, like answering your questions, like generating new content for you. How this all works is basically a bunch of neural networks organized into a complicated architecture that we call transformer architecture. And we'll dive deeper into this as we
go definitely
further in the podcast. But essentially, these complicated neural networks, what they're trying to do is understand how language works. And through complex mathematical computations, they're able to do this. And the biggest difference that LLMs have brought, all of these things, neural networks, transformer architectures, deep learning, all of these things existed since decades.
Yeah.
But what LLMs have brought in is sheer scale. Scale in terms of the amount of data that they're trained on, as well as the amount of connections and parameters that are inbuilt in the architecture.
Okay.
When we talk about the training data, right? Think about LLMs has been trained on a chunk of internet. And you know how many articles, blog posts, Wikipedia articles, n number of things are on the internet. So through basically reading through all of the internet, it's able to understand how we humans talk, think, and basically analyze things.
So how when you say a chunk of the internet, how exactly, like what scale are we talking about in percentage terms?
We're talking about a petabyte level scale, right? So if you think about it, Google has the most amount of coverage of the internet,
Okay.
right? And whatever is not covered by the Google, nobody knows, right? That's your dark web.
That would be the dark web, yeah.
So if you think about the amount of data that Google covers, the observable universe of internet, if you will, then the data sets that are used to train these models are almost ranging around 60-70% of coverage of that data.
Okay. So in petabytes, do you have a sense of what is the exact, like in terms of let's say petabytes? Is it tens of petabytes, hundreds of petabytes, millions of
It's
petabytes?
around tens of petabytes.
Tens of
Just to
petabytes?
give you a reference of that, right? If you take the entire English Wikipedia corpus of articles, that compresses down to 20 gigabytes.
Wow.
And
So
if you take that and multiply that by 1,000, then you
that'll
multiply
be
that again by
terabyte.
1,000, that's when you reach 20 petabytes.
Wow.
That's the amount of data on which some of these LLMs are trained on.
And the LLMs are primarily trained, the ones that you're talking about right now, are they only text-based language models, or are you talking about in the audio and the video as well?
So currently, when we talk about large language models, they are mostly trained using textual data.
Okay.
And nowadays, OpenAI and some other organizations, they've started taking YouTube videos or all sorts of multimedia and transcribing it into text to augment their data sets.
Okay.
In fact, even images are being captioned so that it can be used as a training data as well.
How so?
So images, so what they are trying to do is get as much data as possible in the form of text. Now, media content or videos, it can be transcribed. Videos having audio, it can be transcribed. But images, how do you transcribe the images? You cannot unless you are describing the images, or captioning the images. So they are using the images as well as video data for captioning and transcribing, and then using all of that data to train the model.
How do you, I mean, I understand the part where, you know, a transcript for a video can be written using some kind of a model, and then that can be fed into the large language model as a text, all right? And that can essentially be associated back to the video, and the large language model can understand, okay, these are certain parts that this is where a certain lip movement essentially transcribed to a certain, you know, emotion or a certain piece of text, and that can be associated back to it. But how exactly is that done? How exactly is that labeling done for images?
So there are several companies out there
Yeah.
who do this. They employ human annotators because in order to ensure human level accuracy, you need human annotation, human labeled data. So they, on a large scale, they employ human annotators, and they do this labeling for us.
So they essentially, like, let's say there's a picture of a studio setup, and there are cameramen around it, and then let's say right now what we're doing, there are three people talking. So you'll click a picture of it, and then a human labeler will essentially write down the setting that is out there. All right.
In fact, a given photograph or a given data point is not just labeled by a single annotator. So there is something called as inter-annotator agreement that needs to be inter-annotator agreement that needs to be checked before it goes ahead for training. That's why they employ multiple human annotators for the same data set. For the same data point, and then they check for inter-annotator agreement, and then they decide that okay, which is the correct or the most correct label for this particular data point.
Oh, so there are levels as to how the annotation is done and how it is verified.
If you think about it, there's another process that is often followed in the industry, right? You have a computational model that generates the captions, right? So for the same image, it might generate 10, 20 different captions. And then humans are sitting there and they're like, okay, what's the best caption? What this removes is the subjectivity of each annotator.
Okay.
Right? So the captions are being generated by the models, and then you just have to pick which one describes it the best.
Okay.
And whichever one gets the most votes, for example, then gets selected.
And then let's say we are done with the labeling part, and the labeling essentially will kind of help us build the models such as Dolly. So they will essentially, right?
If you reverse the roles.
If you reverse the roles, then it will help us build
In
Dolly.
fact, there are several methods of doing this as well. So one is the human annotators, they start without anything. They start raw and then they look at it and then like label it. And there is AI assisted data labeling as well, where AI is giving the labels, and then all the humans have to do is review the labels.
Essentially what Palash was talking about right now. Okay. But for that, you have to essentially build out that initial model as well. Okay, got it. Okay, so I understand now that what exactly is a large language model, and the large language model essentially how the data is fed into it, what is the size of the data, and how it's captioned or how it is annotated. That part I think I have a fair understanding now. But if we go into the inner working of the LLM, then how does exactly a LLM work, in the sense that how exactly is its architecture built is what I'm more curious about. So I think a better approach would be if we take a bottom-up approach, where you can probably tell me, from the very basic unit of how the LLM is working or how the LLM is being built upon, and then we probably move to the 30,000 feet view. That might be easier for us to understand, the complexities involved with the LLM building. So,
Sure.
What exactly are your thoughts on that?
So LLMs, they are, in order to understand the whole architecture, we need to first, as you said, understand the processing of it. How are they first processed? How does it consume the data? How was it built? So the most basic part of it is tokenization. So tokenization is nothing but sentences. Let's assume there are like large sentences, but models, they don't understand these large sentences, especially LLMs. They consider subwords. So subwords are basically a smaller unit than words. So for example, there is let's say for example, unhappy. There is this word called unhappy. So how LLMs do it is it does subword tokenization of this word unhappy, like unhappy.
Yeah.
Now, what this enables the LLM to do is it captures the morphological structure of every word, including understands its prefixes, suffixes, the root words of each of the words, each of the tokens. And what it enables the LLMs to then do is it will be able to better capture some other words unrelated, maybe at first glance they are unrelated, but maybe they are related at the root level. Like for example, with unhappy, happily is another word which is related, but it understands that okay, these are words which are actually related because of the subword tokenization.
Okay. And okay, so I understand that, as Rishi said, when there is a word called unhappy and there is a subword tokenization happening, but at the root level, there must be a mathematical approach which is the only language that is understood by the computer. And as I understand, there's a lot of linear algebra in play whenever you're building a machine learning model, which essentially are, the LLM essentially boiled down to be artificial intelligence or a machine learning model. Now, how exactly is that mathematics coming into play? Are there vector spaces? Are there vectors? Are there matrices which are kind of like, is there a technique where you can convert some words into a mathematical representation? Like, how exactly does it play out?
So we've known for ages that
Yeah.
computers don't understand anything but numbers. So in order for us to make computer understand language, we have to represent language in
Yeah. Yeah.
the way this is done is by using vector encodings.
Okay.
Each token, as Rishi pointed out, unhappy, each of these is associated with a bunch of numbers. In modern LLMs, each of these tokens is actually associated with 2000 plus numbers at once. Each of these tokens, their associated numbers, these associated numbers are called the vectors, the encoding vector of a token.
And how exactly are you building? How you exactly, like, even for a subword, how would you build a vector around, let's say, inside that unhappy, where you where Rishi broke it down into 3 subwords, unhappy. So how would essentially boil down to a numeric representation?
The way that works is a concept was introduced, I think, about 7-8 years ago now, or more than that, called word2vec.
Yeah.
Right? The way this worked was that it analyzed every token in its context, right, surrounding words,
Yeah.
and tried to predict basically which words is this token going to be surrounded by.
Okay.
So if you take a piece of text, right, and if you break it down into tokens, you would know which tokens surround which tokens. Right?
Yeah.
So you already have a set of positive examples from which a computer model can learn. Then you can create negative examples by taking a token and giving it a token that it is not surrounded by. So now you have a bunch of negative examples.
Okay.
A machine learning model is then trained on these positive and negative examples. And the weights that the machine learning model comes up with at the last layer, these vectors, these numbers, are essentially used to represent each of the tokens.
Okay.
Right. What's important to understand here is that we figured out a way to represent tokens as numbers while encoding all the syntactic and the semantic information associated with a token.
So you told us about the vector encodings capturing these semantic and syntactic relationships, but I'm a little confused. Like, what exactly is semantic relationship? What exactly is a syntactic relationship? I mean, I kind of understand it in the sense of the natural language like English, but how exactly is that translating to the mathematical representation? If we can focus probably first on the semantic relationships. Yeah.
So when you think about semantic relationships, you have to think about it in the sense of how two words can be related to each other.
Okay.
A very simple example of this is cat and dog.
Yeah.
If you think about the sentences in which cats and dogs are used in, they are often very similar sentences because cats and dog are actually very similar words. They are both pet animals. They're probably both fluffy. They're probably both cute.
Yeah.
Right? So these two words being related is an example of a semantic relationship, wherein two words are related because of their context or because of their meaning.
So when the large language model is trying to understand the semantic relationship, how would it identify these semantic relationships?
Correct. So as I told you during the vector encodings part, right, that the way we train a model to generate a vector encoding is by looking at what words co-occur together, right? What words occur in the similar surroundings. So the surroundings in which the token cat might occur will be very similar to the surroundings in which the token dog might occur, and therefore their numerical representations will be very similar.
Okay. And then is there some kind of a probability model also being built around it?
Probability, no.
Okay, got it.
This is more of a vector space representation. So you have these bunch of 2000 numbers associated with each number, each token. So you take this and if you plot it on the 2000 dimension axis, there will be a point. The points of cat and dog will be very close together because they're very semantically related.
Okay, okay. And then how does the syntactic relationship come into play?
So syntax is essentially what comes after what, right? If you think about it in terms of sentences that we speak, when we are trying to say I am doing something, we wouldn't say am I doing something. That changes the meaning.
Yeah.
Right. So how syntax affects meaning is what syntactic study is all about. And how LLM learns is again, it looks at what tokens surround each other, right? And in what order do they surround each other?
Okay.
So that's how it captures syntactic relationships.
Okay, and again, how is the math playing around it? You mentioned that the vector space is kind of taking into consideration the semantic relationship because two different objects such as cats and dogs are kind of occurring near each other. But then, how would you explain the math around the semantic relationships?
So again, if you think about it, when a word follows another,
Yeah.
right, that is an example that the model will see in tons and tons of training examples that it sees, right? The sentence "I am doing X" or "I am this," "I am that." That occurs infinite number of many times during the training. So the model learns to associate that, hey, these two words are related to each other because they co-occur, and this follows that, because that's how I've seen it in the examples. And when you think about the math of it,
Yeah.
again, these are the encodings are very similar for these two again because they occur in the same context all the time.
Okay. So it's still again purely
Purely
the
based
vector
on the distance
algebra.
between the vectors.
Okay. And the distance representation, is that like what kind of similarity are we talking about? Like how exactly is that distance measured?
So I'll try to do it in 2 dimensions because
Yeah,
it's easier.
yeah.
If you think about this, right? One point could be here. One point could be here.
Yeah.
One point could be here.
Yeah.
A specialty of these vector encodings is that if you take a line from the origin and draw it to the point, the direction of it, or if you think about the angle between any of the axes that it makes, that's how you represent similarity. It's a concept called cosine similarity.
Got
in our
Yeah.
field. But essentially the same direction, representations in the same direction represent very similar syntactic or semantic meanings.
Okay. So you keep on taking like pairwise cosine distances. Is that how it is happening? Okay.
One way of measuring distances. Yeah.
Any other way?
There are other distance measurement techniques, but they don't work very well in language.
Yeah, there are like Manhattan distance, there is Jacquard distance, there is Euclidean distance, but they don't work well as cosine similarity.
Okay. So these distance metrics that you talked about, I know Euclidean distance definitely is something that almost everyone should be familiar with if they are coming from a mathematical background. But the Manhattan distance and all the other distances that are currently being researched upon, like what kind of results have they shown? Have they shown any promising results going forward, or do you think cosine similarity will be the one that will?
I think at least in the near future, cosine similarity is
It's doing a okay.
pretty good job
Okay.
in calculating the similarity between the tokens.
Okay.
So as I was saying, right, if you take the representation of king in this large dimension vector space, and if you move in a very specific direction from it, you will reach ultimately the representation of queen, its female counterpart.
Okay.
Similarly, if you move in that direction from any male token, you approximately reach its female counterpart token.
Okay.
So this specific direction in the vector space represents or captures the male to female relationship of tokens.
Okay. Any other examples that you can give us, Rishi, for these kind of relationships that might be in a natural language?
Yes. So how I imagine these tokens in an embedding form are like a digital footprint in an imaginary world, in an imaginary plane. So just like king and queen, so words that have similar meanings, they tend to come together, like happy, joyful, blissful.
Yeah.
These words, they have a similar meaning. So that's why their digital fingerprint will be somewhere near each other. Similarly, just like he gave example of cats and dogs, words which have similar grounds, pets, camera, tripod, they also come together in the embedding space. They also have a similar digital footprint. In fact, they act as Lego bricks as well. So you can even they also have embeddings for prefixes and suffixes as well, along with the root words. So if you add the digital footprint or the embedding of un with happy, if you add the so it will approximately come near unhappy.
Okay. Okay. So essentially, the vectors are kind of the directions in which different relationships can be mapped. Okay. And apart from the semantic and the syntactic relationships, what other relationships are natural language models, trying to capture?
So, semantic and syntactic relationships we've been able to capture for more than 10 years.
Okay.
It's only recently that we have started capturing contextual information. So, just to give you an example of what this means, if you think about a sentence, the bat is flying.
Yeah.
Right? The word bat, if you focus on that, it can have two separate meanings. It could be the nocturnal animal, the bird that we know, that's bat, or it could be a cricket bat, it could be a baseball bat in the sports context.
Okay.
Right? And which meaning is being used? We humans infer that from the context. Right?
Okay.
If let's say this sentence is preceded by stuff about forest or trees or animals, then we would intuitively know that it's the mammal bat that we are talking about.
Okay.
Whereas, let's say this context is the context is something like Sachin Tendulkar or cricket or any of sports-related terms, then you would know that this is talking about the cricket bat.
Okay, so in a way, it's earlier, the way I'm understanding it is, earlier the associations were kind of, it could go only a certain distance apart, but now it can go a larger distance, both in the past and the present, with relation to a particular word in the entire corpus, and then map out that distance relationship in a better way now, in the past few years. Is that what you're saying?
Definitely, yes. And
Okay.
to add to that further,
Yeah.
before we were able to do this contextual embedding, if you will, contextual capturing of information,
Yeah.
each token was associated with a set of numbers that only represented a generic meaning of that token. For example, at any point in space, there is the embedding of the word dog. You wouldn't know what dog it is. It's just a dog, right? And whatever you imagine first when you hear dog is what that representation means. Whereas if you want to say a black Labrador dog, right? Now all of a sudden you have this context that, hey, the dog is black, he belongs to a very specific breed. So you can't represent that with the generic representation of the word dog. You need to move in that embedding space to come to this specific representation. And that, I think, is what contextual information is all about. And that is the major advantage that modern language models have.
So they're kind of building a memory around the entire thing. Okay. And I believe this is where the attention part comes in.
Exactly.
Okay.
Exactly. So attention is all you need is the paper that
Yeah.
introduces
I think we have all
this,
yeah.
this world.
Yeah,
human,
yeah.
right? And essentially what attention is trying to do is it goes through a context, a sentence, token by token, looks at what tokens influence what tokens in what ways.
Okay.
Right.
Can you explain that a little bit, in more detail?
Yeah, sure, of course. So if you think about a sentence, right, she is eating a green apple, right? If you break it into token by token, as we've learned in tokenization, for simplicity, I'm going to use a word level token. So each word is a token.
Okay.
Right? And if you have represented she with a bunch of numbers, is with a bunch of numbers, apple with a bunch of numbers.
Yeah.
These bunch of numbers at this moment of time represent an apple, not a green apple, an apple. But from the sentence, we know that it's a green apple, right? Now, if you forget about math and computers and everything, if you intuitively look at this sentence, we know that the word green here is an adjective. It's modifying the meaning of the noun apple. That is the kind of behavior that we want our computer models to mimic, right? We want the computer to understand that, hey, this other token is supposed to modify the meaning of this other token in this way, right? And if you talk about math here, then you would say that the representation of apple, we should move from that in a specific direction to come to the representation of a green apple.
Okay.
That is what attention is trying to do. Now, how do we do it is a separate part.
But again, like a green apple and a cat and a dog, they seem kind of similar. That representation kind of seems similar. So when you explain about the mathematical sense of the attention that we are talking about, we know, the position of certain words in the vector space are kind of capturing the semantic and the syntactic relationship. Now, how does that differ from how the math behind attention is being built?
Right. So I gave you a very simple example with one sentence.
Okay.
Right.
Yeah.
Now you can start thinking about it in terms of story.
Okay. That's where the longer memory will come in.
Longer-term dependencies
Yeah.
are captured,
Okay.
right? And that's where you have much larger contexts, maybe spanning paragraphs or pages of a book,
Okay.
right? And the way it works is ultimately, again, going back to the story example.
Yeah.
Let's imagine in some paragraphs before, you understood that whoever is writing is in Kashmir,
Yeah.
right?
Yeah.
So now you know that this apple actually is coming from Kashmir, which you wouldn't have just understood from the syntactic and semantic relationship unless you capture these long-term dependencies.
And that's where you go. And so I believe there must be a lot of compute power also required to capture the entire memory that the large language model is building out.
Yes, definitely. So LLMs, they consume a lot of power. In fact, to capture these nuances of language, it requires like billions of parameters. 170. We must have heard about 7 billion parameter model.
Yeah.
170 billion parameter model. It requires billions of parameters. Parameters are basically like tunable components of a model. And it requires so much power. It has been estimated that, and in order to train an LLM, it requires like billions or millions of dollars of capital, and the power requirement is almost equal to 1 month of power requirement of a city.
Oh. Okay.
Yeah.
So it definitely has a disadvantage on the global warming, on the global
There has
like.
been a lot of controversies around training LLMs because it requires so much power. The amount of carbon footprint that we are leaving with using these LLMs, not just the open source ones, but also the proprietary ones, is huge.
And I believe that is something that is not coming up as much with the hype that is going on with the large language model building, right?
Yeah, that is.
Yeah, I mean, people are generally more focused on what the LLM can do, but what is the actual carbon footprint that we are incurring in order to get to that level of understanding of the language by an artificial machine? That's definitely something that not a lot of articles focus on these days.
Yeah. In fact, there was one not so famous article on this where they were talking about, in fact, the OpenAI guys, they were talking about the type of questions that in the initial release of ChatGPT, the type of questions that people were asking, they were so simple that they could have even Googled it. But still, they were using ChatGPT to answer, like, who is the current Prime Minister of India? They can simply Google it, but they still were going for ChatGPT for such simple queries, and that had a lot of a huge carbon footprint, even for simple questions. A simple question, a simple prompt to a ChatGPT has a lot of carbon footprint.
Okay, I mean the relative carbon footprint must be much higher.
Of course. Of course, Googling also
It has a
carbon footprint, but the delta between both is huge.
Yep. Okay, so we talked about the global warming impact that large language models are having, and we were talking about the attention or the memory building that language models right now are doing. But in terms of the memory building, like what were the key aspects that came before this memory building? I believe there are some language models that existed even before large language models came into the memory aspect of things. So how do you can you shed some light on that?
Sure. So there were not really large language models before LLMs.
Yeah.
There were.
This is just language models.
Yeah, there were models.
Okay.
Actually. It's like it started with statistical models. Like during 80s and 1980s, 1990s, statistics played a huge role in AI.
And that would be, I believe, when the compute was not as much, right?
Yes. The compute at that time was not as much. So, and still they came up with a very beautiful implementation called Ngram model. So, Ngram model, it relies on N tokens for next word prediction.
Yeah.
So, like N is, it can be any number. It can be bigram. So 1 gram. So 1 gram model is, it depends on the current token independently to predict the next word. For bigram, it takes into consideration just the n minus word, the word before, to
Got
predict
it.
the next word.
For two words.
Yeah. And similarly for trigram and
So on and so
on and
forth.
so forth.
Yeah.
And it uses probabilistic models, probabilistic distribution models like hidden Markov model. IBM came up with their own probabilistic models, IBM models during that time.
Okay.
So this was a whole different phase of statistical models that was being used in NLP during that time.
So the memory that they could capture back then was only up to certain number of words that they could go back in time.
Yeah.
Okay, got it.
And then as time progressed, by like 1997 or so, they came up with a paper which was LSTM, which introduced the concept of LSTMs.
And LSTMs are long short-term memory networks. Okay.
Yes, that's right. So
Yeah.
LSTMs are long short-term memory. They are a type of RNN models, but they solve this problem of RNNs of vanishing gradient. So for like longer sequences, RNNs when RNNs train on longer sequences, the gradients, they become infinitesimally small. So in order to tackle this problem, LSTMs came into picture.
Got it.
It uses memory cells, it uses gating mechanisms as well in its architecture. So it basically tried to solve the long sequence problems.
Okay, so the longer memory that was not being captured by Ngram earlier. So
Interestingly, in fact, in 1997 when the paper came out, they did not realize LSTMs as something that could solve this problem for NLP.
so what were they being used for?
So they just did it for long sequences.
Okay.
They did not realize back then that, in fact, in its paper, it never mentioned that this will be like a game changer in NLP. They were trying to solve long sequences problems. Long sequences can be not necessarily like words, it can be any sequence.
Any sequence
They
in the
realize that, hey, words, language, they are sequences in itself.
Yeah.
Why not let's try LSTM for texts? And then they discovered, yeah, it works for text as well.
Oh, that's nice. Okay, so we kind of came to that memory aspect in even LSTMs, right? I mean, it has the word memory in it. But I believe, like as Palash was mentioning, so the memory aspect that is being captured now must be infinitely much better than how LSTMs must have captured it back then. How would you, like, what exactly is it that they are doing differently if we actually start going into the math behind things?
So one of the major problems with LSTMs was that they were still using sequential modeling.
Okay.
They were processing tokens one by one by one by one by one.
Yeah.
Right? And obviously they didn't have that much compute power at the time to do a lot of research into this. But what modern architectures do differently is that they use parallel processing to do all of these.
And parallel processing meaning as in the computing sense, or is it in some kind of a different architecture?
No, so both.
Okay.
So obviously you are able to distribute your computations on different CPU cores, cores, run multiple GPUs in parallel, right? That's something that's possible now, not possible back.
Yeah.
But in order to leverage that, you have to modify your architecture and the way in which you do computations so that they can take advantage of these parallel processing techniques.
And is that where the transformer model came into?
Exactly.
Okay.
That's so even back in when LSTMs got started using for this NLP tasks, right?
Yeah.
They were using attention layers.
Right? Okay.
Attention as a concept was introduced in 2015, not in 2017, surprisingly.
Okay.
And they were using attention layers followed by LSTM.
Okay.
Again, sequential.
So they were trying to get there in a different way using LSTMs, but not the transform.
And they realized that it's not the attention layer that's the problem computationally.
It is the LSTM. Got it.
And that's where the 2017 paper came in. Attention is all you need. They
Yeah.
removed the LSTM layers
Yeah.
and they replaced it with simple multi-layer perceptrons,
Okay.
right? Neural networks.
Yeah.
And they changed the way the math is being done to
Yeah.
leverage the parallel processing. And that's, I think, where the whole large scale comes from.
And that math around that large scale is essentially captured in the transformer architecture.
Correct. Yes.
Okay. So how exactly, like, can you give me a brief overview of how you understand the transformer, a simple transformer?
Yes. So we'll start by talking about how attention works.
Yeah.
Right. And then we'll look at it in the holistic picture of a transform.
Okay.
Right. As I talked about it previously, what attention is trying to do is understand what words affect the meaning of what other words and how do they affect it.
Yeah.
Right? That's the broader objective of attention. So to do this, we'll start again at the very beginning of the LLM architecture. We started with the tokenization. We've given a bunch of numbers to each of these tokens, right? Now, at this moment of time, these numbers only represent the generic meaning of that token. And our job is to take it from this generic meaning to a contextualized meaning. The way we do this is, mathematically speaking, we give each of these tokens 3 separate vector representations.
And those vector representations.
In a very natural language, they're called the query vector, the key vector, and the value vector. We'll
Okay.
dive into each of these individually.
Okay. Sure.
We'll start with the query vector, right? In a layman's term, you can think of this as if the word dog has a query vector, then it represents or encapsulates the generic meaning of a dog, along with what can this word be influenced by, right? So, as an example, if you know language, nouns are often influenced by adjectives, right?
Yeah.
So the word dog can be influenced by a word like black before it or a Labrador before it. Right? So adjectives modify nouns.
Yeah.
So a query vector of a noun will represent that. It will say that, hey, I'm a noun and I can be influenced by adjectives.
Okay.
Okay. And the way you compute this query vector is by multiplying the vector representation of the token with a weight matrix. Weights are nothing but tunable parameters of a model.
Okay.
And these parameters you learn during the training process.
So weights are essentially, like we all know, like weights in any machine learning model is what is the thing that we end up learning.
Exactly.
Got it. Okay.
So these learnable weights, we take the vector representation of the token, we do a matrix multiplication, and it's important that we do a matrix multiplication because that's what takes you to these parallelized architectures, right? You're able to do independent matrix multiplications without having to go through tokens sequentially.
Okay.
Right?
Got
So
it.
it's an important part to understand. So you do this matrix multiplication and you arrive at a query vector.
Yeah.
Right, which again represents that I am this and I can be influenced in such ways. Then to each of the surrounding tokens, you give another vector representation called the key vector,
Okay.
which says I am this and this is how I influence people or influence tokens. So you can imagine that if you are giving the query vector, the key vector to an adjective, it will say, hey, I am an adjective and I influence nouns. So now if you think about it, you have this query vector that says, I can be influenced in these ways. You have a key vector that says, I can influence things in these ways. If you compare the two, and if you find similarity, then you're bound to end up in tokens that can influence each other.
Okay.
Right? So what you have done is you have created a query vector, you have created a key vector. And now if you want to assess similarity between two vectors, what do we use? We use cosine similarity. So we do a dot product. That's how cosine similarity is calculated, right? We do a dot product between these two vectors. And we arrive at a number that we can then scale into 0 to 1, right? And that ultimately gives you how much any particular token in the context influences the token that you're analyzing.
And that arriving at that 0 to 1 representation, like what techniques are we following there?
So you have a bunch of numbers that come from the dot product.
Yeah.
You normalize them and then you apply a softmax function.
Okay.
Very simple softmax
So
function.
the normal.
Puts it into a probability distribution.
Okay. Okay. And the probability distribution will help us how at the
So
end?
it assigns a number between 0 to 1 to each token, measuring how heavily does this token influence the token that I'm analyzing.
Okay.
Right? So in the context of she is eating a green apple, the word green will have a higher score of influencing apple
Got it.
as compared to is or a or eating.
Got it. Got it.
Right?
So, an apple can be like when attention comes into play. What you're saying is an apple, she, green, eating. All of these can influence the word apple, and green here is kind of if let's say green is the actual word that is influencing it the most, then green is the thing that is actually influencing it the most, and that will be the probability score that will be attached
Yes.
from apple to green, from apple to she, and from apple to eating.
Correct.
Got it.
Right? But now what you have done is you have understood what words are
Yeah.
relevant to another words.
Okay.
You still don't know how they modify the meaning.
Okay.
Right? You only know that green influences apple. How?
Yeah.
So that's where the third vector representation comes in, the value vector.
Value vector.
So the value vector can be seen of in a way that, hey, I am this, and when I influence someone, this is how I modify them.
So up to this point, you have told us about the key and value vectors that come into play in the transformer architecture. How does it build upon that? Is that all, or are there other layers to it?
There's more, right? So until now we were talking about how we get to know which words influence which other words.
Yeah.
Right? It's also important for the mechanism to understand how much, by how much. And the general picture again that you are trying to go to is in that vector space, how much do you move a point by and in which direction so that you represent this contextualized meaning. Right?
Okay.
So that's where the third vector representation comes in. It's called the value vector. So
Okay.
we've talked about the query, we've talked about the key, now it's the value vector. What this value vector represents is that if I am a token, my value vector will represent that how much and in what direction will I take another token if I am relevant to that token.
And how does it help the transformer architecture?
So essentially the way it works, right? Every surrounding token has a value vector.
Okay.
And we've already calculated a number between 0 to 1 to determine the influence.
Okay.
So what you do is you multiply these weights by the value vector of the surrounding tokens.
Okay.
Right? So what you're trying to do is basically weight the value vector. Right?
Okay.
So if let's say that in isolation, the word black would have taken the word the dog from here to here. Right? Because the word dog is being influenced by all these other tokens, it wouldn't fully go there. It would go somewhere in the middle. So, and that is determined by the attention weight that you are giving it.
Okay.
Right?
Okay.
So what you do is you take the value vector, you multiply it by the attention weights, and you basically just add it onto the encoding vector of the token that you're analyzing.
Got it.
And now this new encoding vector represents a contextualized meaning of the token that you were analyzing. So you have gone from dog to a black Labrador dog.
Okay. Now, it still seems like a black Labrador dog is just a single unit of something which is bigger, which is capturing the bigger picture. Am I right?
Yes, that is correct. In this simplistic example to educate,
Yeah.
we chose a sentence,
Yeah.
we talked about a token.
Yeah.
And this is what's happening just within one single block of attention.
Okay. So there are different blocks of
Multiple
attention.
blocks and multiple attention layers within the same block.
Okay.
Right? So this, what I just explained to you is a single head of attention existing within a single block of attention. A single block.
Sorry, if I may interrupt. So, how is a attention head and an attention block, like how are they interrelated?
So attention blocks are basically one operation of attention, right? And within this one operations, you run in parallel 96 different heads of attention. So one head might be looking at, let's say, the adjective-noun relationship.
Okay.
Another head might be looking at the noun-verb relationships.
Okay. So it's something similar to a convolutional neural network where, different convolutions end up capturing different parts of
things, yes.
Yeah, okay.
Yes. And because these all operations are matrix operations,
Yeah.
they're independent of each other,
Yeah.
all of these 96 heads are running in parallel,
Okay.
which gives you efficiency in terms of computational power.
Okay.
right?
Like, is it so that running in parallel is also like there's a architecture around the computing as well, or are you talking only about the algorithmic compute?
This moment, I'm just talking about all the computations that are happening because of this matrix multiplications.
Okay. Oh, so it's a mathematical parallelism that you're talking about, not the like the computational parallelism. Okay.
In order to enable computational parallelisms, your operations must be independent of each other.
Okay.
And that's where the way we are leveraging the three separate matrices comes in.
Okay.
That's why you're able to do such computation at such scale.
Okay. And probably even faster, I guess.
Even faster.
Yeah.
Even faster.
Got it.
Because the concept of matrix multiplication has been solved ages ago.
Yeah.
Very fast at doing it.
Yeah.
There are specialized libraries even
Definitely,
nowadays that do this.
Okay.
So what you have now ended up with is you have learned the context,
Mm-hmm.
right? So initially in the first block of attention, if you will, you only understand shorter term dependencies like, okay, noun, adjective, noun, verb, nearby, right? Then this is still one half of the first transformer block that we are talking about. Right?
Okay.
There are 96 such blocks.
So transformer block or attention block?
You have a transformer block. Attention is just one half of it. You have another block of computations happening called the multi-layer perceptron.
Okay.
That's interchangeably used as a feed-forward network.
Okay.
Essentially, during the attention block, each of the tokens are talking to each other, influencing each other. But in the MLP block, you start analyzing these contextualized tokens on their own.
Oh, okay. So, like, can you give me a practical example of how that MLP block might actually be playing into learning that, like, you know, the different attentions that are happening in this entire?
So, we've all played the game of charades, right?
Yeah, yeah.
Wherein you would guess a word or guess a movie within the person who's acting, and then they would allow the group of people to ask questions, yes or no questions, to guess the word that you have thought of.
Yeah, yeah.
Let's try that. I'm thinking of a personality right now, and your job is to guess what personality. In order to do this, you can ask me yes or no questions.
Sure. Are you human?
Yes.
Are you female?
No.
Then you are a male.
Yes.
Are you a citizen of the United States of America?
No.
Are you a citizen of India?
Yes.
Are you between the ages of 0 to 10,
No.
10 to 20,
No.
20 to 30,
No.
30 to 40,
No.
40 to 50, 50 to 60, 60 to 70,
No.
70 to 80?
Yes.
So you are old.
Yes.
Are you a politician?
Yes.
Are you the Prime Minister of India?
Yes.
Are you Narendra Modi?
Yes.
Okay.
So what happened here is that there is a token, Narendra Modi,
Yeah.
and you are asking it a bunch of questions to know more about it,
Okay.
right? That's what a multi-layer perceptron is supposedly doing. It's taking each individual token and it's asking all of these questions in the form of mathematical non-linear transformations, right? So you
Okay.
know how in neural networks you have all of these transformations that
Yeah, yeah.
and at the end of it is a ReLU activation function that gives you a 0-1 output, right?
Yeah.
So that's what's happening in the MLP layer, that you are trying to take each token and trying to understand more about it by all of these questions.
Got it.
What you end up with is contextualized and factual information all at the end of this transformer block.
Okay. Okay. So, and that's like in the end, you kind of end up interconnecting all the different transformer nodes that are, you know, running in parallel, and then you get to your language model.
In GPT-3, for example, there
Yeah.
were 96 transformer blocks,
Okay.
each with 96 heads of attention.
Okay. So that's definitely a huge scale.
Yeah, that's huge. In fact, when GPT came out, that was the point where LLMs actually became famous. Until that point, before GPT came out, we were only talking about language models because the scale was not as large. But when GPT-1 came out, GPT-1, 2, 3 came out, That's when they said that, okay, these are no longer, looking at the scale, these are no longer language models, these are large language models that we are dealing with here, LLMs.
Okay, so that's where the terminology has started getting stuck in the marketing sense.
Yes.
Got it.
Even if you think about GPT-2 and GPT-3, right?
Yeah.
GPT-2 produced almost garbage output.
Yeah, I've seen the videos of GPT-2.
But all that changed between GPT-2 and GPT-3 was large.
Yeah.
More parameters, more training data. And deep learning is probably one of the only branches of AI that has proven to scale very well with data. Oftentimes you start getting diminishing returns. With deep learning, there is no such thing.
Yeah, with deep learning, larger is better.
I think that probably follows with almost everything in life. It's just a matter of fact. It's just a matter of how large you can make it computationally, I guess. Okay, got it.